All right, boys and girls. Today is all about systems of equations. We're now at day 13, so we're 13 days away from the SATs in September. And system of equation will be our next topic. This is one of the most tested algebra topics on the SAT. If you have been to the exam, you might have noticed. System of equation questions can usually pop up in pure algebra questions or word problems, sometimes even geometry like lines and slopes. Now, usually they're pretty straightforward, but sometimes they can be wrapped up in a bit of wording that you have to weed your way out. And my hope is that by the end of this lesson, you'll be able to actually at least recognize what methods and ways you can use to solve these questions rapidly. And in today's session, we're going to cover, I think, four things. And first one will be solving systems with substitution and elimination, and then translating word problems into systems. This is a big one because SAT has a lot of these questions. The third one will be recognizing special cases when you have no solution or infinitely many solutions. And the last one will be looking into cases where we're not dealing with just linear equations alone. There's a combination of linear equation and a quadratic equation. First thing we're going to discuss is solving problems with substitution or elimination method in systems of equation. Now, whenever I'm talking about this topic, students are asking, why can't we just use Desmos? Well, you can obviously use Desmos. I like to think of it as there's three ways to solve systems of linear equations in SAT exam. One is Desmos, other one is substitution, and other one is elimination. Now, not always Desmos will give you the quickest answer. Now, since SAT is all about the speed, it's good to know all three of them because sometimes questions are designed in a way that substitution or elimination can be much quicker than typing to equation and just messing with the calculator. But it all comes to a personal preference, whichever way faster for you. Some students prefer doing it quickly on paper if it's a very easily recognizable question, and some people prefer to do it on Desmos. Or you can do both, do it on paper and quickly check with Desmos, which wouldn't be the most efficient, obviously, but just to be sure if you have enough time. So let's look into how can we solve these questions using substitution or elimination method. Now, if you remember, I don't want to go to too much details because this is designed to be a review sessions. Substitution is when you are isolating x or y and representing, for example, x with y, and then substituting that into another equation. And elimination is when you are adding or subtracting two equations if you see that will make things easier for you. Now, I've got a question here, and this question is actually a good example of both substitution and elimination method. Let's look into the substitution method first. Okay, that's very thick pen. There you go. So the substitution method first. Now, how do I know substitution method could be quick? Because one of the variables, to be more specific, y in the second equation has no coefficient, which means I can directly find what y is equal to from this equation, and that's going to be 6x minus 5. Now, all I have to do is plug that y value into the first equation, and in fact, we can actually divide this by 3 to get 2x plus y equal to 11. That will make things even more easier. Now, 2x plus 6x minus 5 is going to be equal to 11, and 8x is going to be 16, and x is going to be 2. And if x is 2, y going to be 6 times 2 minus 5. That's 12 minus 5, and that is 7. Okay? So I got my answers, which are 2 and 7. Looks like it's B. We can confirm that with Desmos soon. But let me try, so that was a substitution method. Let me try the elimination method as well, just in case people prefer that. elimination method. Now, again, I'm looking at my equation here. Let me rewrite that actually for us. So we've got 2x plus y after dividing by 3 and 6x minus y equal to 5. So when I'm looking at this equation, I see that there is plus y and minus y in these equations. So that means if I just add these two equations, the y's will go away, right? If I add these equations, I'll have 8x plus y minus y, they will cancel out, equal to 16, x is equal to 2. Now, I claim that might be much quicker than writing it out decimals, but again, to each his own. Y again is going to be 7. Now let's try that with decimals as well before we move on. So alright, 6x plus 3y equal to 33, and we have 6x minus y equal to 5. So the intersection point 2, 7. So we are correct, so the answer is B. Again, this is a preference thing, whichever one. Some people, I've seen a lot of people actually are much quicker on paper, although it's fading away a little bit, but good to know all three, because all three can get you to the answer that you want. Now we're going to talk about word problems in systems of equations. Now usually SAT likes to disguise some algebra with basically like a wordy story, but when you boil it down it becomes a very simple equation. Now the key here is to identify what your variables are, so you know what you're looking for. And what I like to do is when I read the question, I just highlight whatever I have numbers and keywords potentially, and that really helps me to put it into an equation. So there's not much theory to talk about here because we already know how to solve systems of linear equation, but rather just practicing with these word problems. So I've got a few here for you guys. So let's see how we can approach them. A nursery sells fertilizer in 25-pound bag and 100-pound bags. Now again, usually in these word problems, you're dealing with two things. It could be a problem like this one, or it could be selling adult tickets or student tickets. Again, there's always two things. Why two things? Because in systems of linear equation, we're dealing with two variables, at least at this stage. If Juliet bought 13 bags of fertilizer for her landscaping business that contained 775 pounds of fertilizer, how many 100-pound bags did she buy? Okay, now there's a lot of numbers that they're throwing at us, but we need to come up with what our x and y is. Okay, so we know that we have two types of bags. I'm going to explain it a bit longer, but just so you get used to it. So we have two types of bags, 25 and a 100-pound bag. If Juliet bought 13 bags of the fertilizer for her landscaping business that contained 13 bags contains how much? 775 pounds. Now we don't know how many of small one, how many of big one. Okay, so some combination of the two gives us 775. So if we have, say, X amount of 25 bags and we have Y amount of 100-pound bags, some combination of that should give us a total of 775. Okay, and we also know that we have 13 bags total. So let's try to come up with our equations. X and Y represent 25 bag and 100-pound bag respectively. So X and Y, the number of bags, equal to 13. Why 13? Because we have 13 bags. Yes? And now, the second equation is how many bags will add up to 775. So if I buy X amount of 25 bags and then Y amount of 100-pound bags, that should give me 775. Fair enough? So that's going to be my equation, right? Now, if I solve this equation, I will get, what will I get? I'll find x and y. I'm looking for y because I said y is representing the 100-pound bag. So, again, we can use a substitution or elimination method, but I'm going to try decimals here. X plus y equals to 13 and 25x plus 100y equal to 775. I see there's an intersection point here. Let me zoom in into that a little bit so you guys can see. What is it? 7 and 6. 7 and 6. So 7 bags of 25 and 6 bags of x equal to 7 and 6 of 100-pound bags. So the answer is going to be B, 6 100-pound bags. All right, I got another word problem here. It seems like, I haven't read the question, it seems like we are asked to construct the system of equation, not really solve it, but construct it, which makes our job a little bit easier. Okay? So let's read carefully. Let's read carefully. A pet supply store maintains an inventory of certain brand of dog food in 15-pound and 30-pound bag. Again, it's the same type of question. We have two types of bags, 15-pound and 30-pound. The store pays $0.6 per pound for the 15-pound bag. So this one is $0.6. This is for 15-pound bag and 50 cents for 30-pound bag. The store's current inventory of this product is 32 bags of this dog food for which it paid 408. So there's total of 32 bags, right? Total of 32 bags, and they add up to 408. Which of the following system of equations can be used to determine the number of 15-pound bags and 13-pound bags? They call them S and B. So this one is S, this one is B. Again, it's the same question. How many total bags we have? We have, how many? 32. Yes? So S plus B has to be equal to 32. That's total amount of bags. Now, how do we get the total cost? So total cost or amount is $408. Okay, and how do we calculate it? For 15-pound bags, we multiply them by 0.6, right? So we don't know how many 15-pound bags we have, but if we did, we called it S, right? So if we know how many bags we had, which is S, then we would multiply that with 15-pound. That's going to give us the total pound, total weight. And then we're going to multiply that by the amount, which is going to give us the total amount for total of 15-pound bags. We're going to do the same thing for the other one. So we got 30, because it's a 30-pound. Let me write B first. So B times 30 times 0.5. Okay, so if we do an algebra here, this is going to be, this one looks easier, B times 15, B times 15, and 15 times 0.6 is what? 3 divided by 2, it's 9. So 9S plus 15B is equal to 408. Looking at my answers here, 9S plus 15B. Looks like it's A. Okay, now again, let me go over the second part one more time. Why do we get S15 0.6? So if you are buying 3 bags, I'm going to write it at the top here. Let me change the color so you don't get confused. If you're buying 3 bags of, I don't know, dog food, yes, and each bag is 10 pound, and 10-pound weight, and they cost you, I don't know what dog food costs, let's say $5. How would you calculate your total cost? It would be 3 bags. Actually, let me do it this way. So one bag costs, actually, wait, not $5 for the bag. Let's put it $2 per pound, right? So if I'm calculating the total cost of one bag, it's going to be 10 pounds times $2, right? Why $2? Because every pound is $2. And one bag is going to be 20. But I have 3 bags, so 3 bags is going to be 3 times 10 times 2, and that's going to be 60. It's the same idea here. So the S is how many bags we have. This is number of bags. This is how many pounds each bag is, and this one is the price. Okay, so hope that one makes sense. In this part, we're going to discuss special cases when we have no solution or infinitely many solutions of systems of linear equation. Now, if you've watched day 15, if I'm not mistaken, where I talked about linear equations and how they are related to system of linear equations, in a sense that if we are solving a system of linear equation, what we are basically doing is finding their intersection point, assuming there is one, right? But not always we have one solution. Now, we can't really have two solutions, I guess, if we're dealing with linear equations, because if we're talking about 2 straight lines, there's only 3 possible cases, right? What are those 3 possible cases? So case one is when they are actually intersecting. So it looks something like this. So whenever they're intersecting, they intersect only at one point. Now again, why one point? Because this is not a straight line. If we had one straight line, one not straight line, then we would have more than one solution or intersection point. But if we're dealing with linear equations or linear system of equations, if they are intersecting, there will only be one intersection point, right? So case 2, what's case 2? Case 2 is when your lines are parallel to each other, right? Which means they're not cutting each other at any point. This is when you have no solution. No solution, right? And case 3 is when your lines are, I don't know how to show it here, but this is what I'll do. When your lines are on top of each other, exactly same equations, basically. That's when you have infinitely many solutions. Infinitely many. Okay? So, and if you remember from the first day 15 linear equations lesson, when do we have no solution? When they're parallel. How do we know if lines are parallel to each other? So if this is y equal to mx plus b, let's call this one y1, and y2 is equal to, again, m1, b1, m2x plus b2. So the lines are parallel to each other when you can write this equation in this format, and m1 is equal to m2. m1 is equal to m2. So if you can bring your systems of linear equation into this format, which is y equal to mx plus b, and you see that the coefficients of x's are same, then you will know that these lines are parallel to each other, which means you have no solution. Now, unless if everything in these equations are same, not only they're parallel, but they're also the same equation, which takes us to case 3. That's infinitely many. Okay? Here's what I mean. I want to show that to you. So y equal to 2x plus b. 2x plus 4, let's say. And y equal to 2x plus A. Now I'm going to add a slider to A. So this is when you have two lines that are parallel to each other. So this has no solution. But if I move this slider up and down, there will be a case which is right here. When these lines are on top of each other, that's when we have infinitely many solution. That's all I meant. Okay? So no solution, no solution. There we go. Infinitely many solution. Again, no solution, no solution. Okay? So let's see if we can solve some problems. Let's try to solve this one. We've got systems of linear equation again. Seems like we have an unknown here. If A is a constant for the given system of equation above, for what value of A will the system of equations have no solution? System of equation has no solution. Now, when do we have no solution? When these lines are parallel to each other. Okay, so if we can rewrite this equation in terms of y, like I mentioned, y equal to mx plus b, we can clearly see what should be the value of a. So let's transform them. Again, I'm trying to bring them into y equal to mx plus b. Okay, so the second equation is almost like that. So if I write, let's start with the first one. So I've got 14x minus a times y equal to negative 9 over 2. Now a is extra here because I need y to be standalone. Nothing, no coefficient. 1, basically. Nothing but 1. So I'm going to divide everything by a here. So I'll got 14a times x minus y equals to negative 9 over 2a. Okay? And I'm going to rearrange this and write y is equal to negative 14 divided by a times x and plus 9 over 2a. Okay, so that's my first equation. And the second equation, I'll just move it around. It's all, the y has a coefficient of 1 already, so I just need to move things around. Y is equal to 7 over 2x plus 1 over 4. Okay, now, like I mentioned, for these lines to have infinitely many solution, or no solution rather, sorry, because the question says no solution, this one should be equal to that, and this one shouldn't be equal. Then we'll have infinitely, then the lines are on top of each other, right? So, now we're just back to doing simple algebra. 7 divided by 2 should be equal to negative 14 divided by a. Yes? If I did everything right. Let me check that. 7 over 2x plus 1 over 4. I think I did. Okay. So, to find a here, all I need to do is cross multiply. So 7a is equal to negative 28. And a is going to be negative 4. And I still need to check to make sure the other one is not the same. So if I plug in a to 9 over 2a right here, this is going to be 9 over negative 8, which is not equal to 1 over 4 here. So they're not equal to each other. So I'm okay. I'm okay. But seems like we did something wrong because there's no negative 4 in the answer. So let's see what the case is. Let's see what the case is. I'm checking my first equation. I think this is the one. So when I moved this, I'm talking about this one here. When I move things around, the 14x should be positive actually. 14 divided by a should be positive. So this one should be positive. And these ones are positive. Yes. So the answer is C. All right. Lastly, we're going to look at a different type of questions. Now, sometimes SAT can literally throw you a curve when it comes to systems of linear equations. well, in that case, it's not a linear equation anymore, but it really doesn't matter. If we're talking about system of equations, again, all we're trying to find is the intersection point. So if these two lines or curves, or doesn't matter, are they intersecting at any point? Now, when you're dealing with a line and a quadratic equation, there's a few possibilities that you can have. So a case one, these are not in any sequence, I'm just saying. Case one could be when you have a parabola and a line that cuts it in two places, so two intersection points. Okay, you can have a case two, when your line only cuts it once. It looks like some sort of devil's stick, but there's only one intersection point. Yes. And case three, when your line and the curve or parabola doesn't interact at any point. There you go. No solution. So the only thing you might remember is you can, of course, do the algebra and find your answer, but also you can think of if we're talking about line and a parabola, so linear and quadratic equation, if the line is above the vertex, if it's an upwards parabola, if it's above the vertex, then you will have an intersection point. If it's below the vertex, you will not. And if you're dealing with downwards parabola, then if it's below the vertex, then you'll have a solution, one or two. And if it's above the vertex, then you have no solution. Try to visualize that. Let's try to solve this question here. For which of the following values of m and b does the system of equations have exactly two real solutions? Now, we have line and quadratic equation. For them to have two real solutions, our line needs to be above the vertex, right? Now, we can plug in the values and see. We can even plug into decimals and try out a few things. Let's see if we can do that actually. So y equal to b plus 5, and y equal to mx squared. Okay, so if I slide m, if it's downward, so if it's negative, then we will have no solution, right? We'll have no solution because they will not intersect, as you see from the graph. So it needs to be an upward parabola. Yes, let me actually move it a little bit here. So you see, if it's negative, then no good. It should be positive for them to have two solutions. Okay, that's good. So that can eliminate some of the answers, right? So m cannot be negative, so we can get rid of a and b. Okay, now we have, at c we have b is negative 10 and b is negative 6. So let's check that out. Let me call this one, let me actually try these values. So negative 10. So negative 10, you see that it's below the vertex. So if b is negative 10, the equation becomes y equal to negative 5, and that is below the vertex, which is 0, 0 of this equation. Well, actually not 0, 0, because m is now 2. Oh yeah, it is 0, 0. Yes. And if we have negative 6, then it will become what? So if m, this is going to be negative 6. And this is going to be, actually this one also doesn't cut it. So we must have done something wrong. We must have done something wrong. What is it? Let's see. So, okay. So if our line is below the vertex, then maybe actually m should be negative for them to have two. Okay, yes. So why I said this one. Now the reason I don't edit out this parts of the video is because this is how a learning process goes, right? When you solve something, you run into problems and then you figure out what went wrong and etc. So now, if we are dealing with an upwards parabola, right, then this should be, what I said still holds correct, right? But now, if our m is going to be negative, then for me to have a two-real solution, my line needs to be below the vertex. So for that, b needs to be, so b plus 5 needs to be negative. So it could be this, right? It could be that, or it could be, this has two solutions, and it could be, so m is -1, they say, -1, and this is going to be -6. Okay, so this is one solution. Okay, so in A we have -1 and -6, which seems to be the correct answer. In B we have -1 and 10. -1 and 10 is not going to work because now the line is going to be above. So this is -1 and 10, but -6 should do the job because now it's below the vertex point and also parabola is facing downwards, so we should be all right. But again, I did it the long way, made a mistake. But you could just plug in the equation to the Desmos, try out the values. That'd probably be the quickest way. But I'm trying to show you and try to explain a bit of the essence of the topic as well. But yes, there you go. That is going to be the end of this systems of equations day. And we are in day 13. Tomorrow we're going to have another topic, day 12. We're getting really close to the SAT exam, so make sure you keep practicing a lot, and if you have any questions, leave them down in the comments and I will try to answer them to the best of my ability. And I will see you guys in day 12. Peace.